Hi, I'm Melanie Kembus, and I'm going to talk to you about massively parallel correlation clustering on bounded Arboricity graphs. This is a joint work with Davin Cho, Havo Miikonen, and Yara Uitto. The massively parallel computation model is a model in which we consider a large input graph. The goal is to solve a problem on this graph using a collection of machines working in parallel. The main restriction is that machines have a limited local memory S. Since we are working in the sublinear regime, this memory is going to be sublinear in the size of the input, in the number of nodes, so n to the epsilon, where epsilon is an arbitrary constant between 0 and 1. The global memory has to be larger than the input size in order to solve the problem, but we want it to be as small as possible. In our paper, we use O of n to the 1 plus delta global memory and even reduce it to O of m log n by sacrificing some time efficiency. When we run an MPC algorithm, the input graph is partitioned among the machines, then each of these machines can do some local computation, and then there is a synchronous communication round in which they can send data to any other machine. This process is repeated until the end of the algorithm, the only limitation being the spacebound S. The goal is then to minimize the number of communication rounds until we solve the graph problem. I will now talk about some known techniques that allow the simulation of local algorithms in the MPC model, drastically reducing the number of communication rounds needed. I will briefly present the local model, since we are going to see some connections between this model and the MPC model in this talk. In the local model, we have again an input graph with n nodes and m edges. But now, instead of applying several parallel machines to solve a problem on this graph, the computation is actually done by the nodes of the graph. So this time, the computation isn't global, but depends on the topology of the graph, two nodes being able to communicate if and only if they are neighbors in the graph. Again, we proceed in synchronous rounds, but this time, there are no space bounds on the local memory of each node. There aren't any bounds on the size of messages either. What really matters here is the locality. Here, we again want to know how many rounds are needed to solve a particular problem. In the local model, a T-round algorithm is equivalent to a process where each node can decide once it knows its T-hop neighborhood. What an MPC algorithm can do is try to gather the T-radius neighborhoods onto machines and then decide on the output locally. If the local memory is sufficient, this is possible in log T rounds. To gather the neighborhood, a node can find out who its neighbors are, then it can query all the nodes at distance 1 and ask for their one-hop neighborhood. We now have the two-hop neighborhoods and can ask for the two-hop neighborhoods of the other nodes and learn the four hops neighborhoods, and so on. If the D-hop neighborhoods don't fit in a single machine, it is possible to gather smaller L-hop neighborhoods, simulate the first L rounds of the local algorithm, and then repeat the process until all rounds have been simulated. Now, what is the correlation clustering problem? It was introduced by Bansal, Bloom, and Chola in 2004, and the simple formulation is the following. Considering a complete, simple, undirected graph, each edge is given a sign plus or minus, indicating if two nodes are similar or dissimilar. The goal is to partition the nodes, avoiding as much as possible to separate similar nodes and to put dissimilar nodes in the same cluster. This is called minimizing disagreement. As you can see on the picture, we have a clustering in red. The edges V1, V2, V4, V5, V1, V4, and V1, V5 produce positive disagreements, and the edges V2, V4, and V1, V3 produce negative disagreements. In total, this clustering in red has a disagreement of 6, which is not minimum, since taking the trivial clustering with only one cluster containing all the nodes would only have a disagreement of 4, since there are 4 negative edges in the graph. For the rest of this presentation, most of the time, we will omit the negative edges and only consider the graph induced by all nodes and positive edges. For this paper, we looked at the simpler case where the graph induced by the positive edges has bounded arboricity. The arboricity of a graph is the minimum number of forests that are needed to cover the graph. These bounded arboricity graphs often appear in natural settings. One issue is that low arboricity graphs can still have high degree nodes. For example, a star is a graph with arboricity 1. But the bounded arboricity actually allows us to take care of high degree nodes separately. A simple and commonly used algorithm to solve this problem is the pivot algorithm. It was introduced in 2005 by Elon, Charika, and Newman. The idea is to pick a random node, then form a cluster with this node and its neighborhood, and then repeat the process on the remaining graph until no node is left unclustered. Here you can see the resulting clustering from executing pivot, first on V3 and then on V4. The direct neighborhood of V3 is V1, V5. The first cluster to be formed is then V1, V3, V5. Then only 2 nodes are left to be clustered. So even if V2 and not V4 had been chosen, the result would have been the same. Notice that the disagreement produced by the optimum clustering on the left or by the clustering on the right are the same, even though the 3 disagreements on the left are positive disagreements, but on the right, there are 2 positive disagreements and 1 negative one, since V1, V5 is a negative edge. This algorithm has been proven to be a 3 approximation of an optimum clustering. This algorithm can actually be simulated by a greedy maximal independent set algorithm, since the processes are similar. Indeed, each time a node is picked uniformly at random, and a node and its neighborhood are taken out for the rest of the execution. This is why we addressed the greedy MIS problem in our paper. In the distributed setting, there are few algorithms that give constant approximations, and they are all inspired from the pivot algorithm. In our paper, we take the log n in the complexity of these algorithms down to polylog log n. Our main result is an algorithm giving a 3 approximation in expectation that runs in O of log delta polylog log n rounds in the sublinear memory regime. This works in 2 main steps. We first take care of clustering the high degree nodes of the graph separately, and second, we simulate a pivot algorithm on the remaining graph by using a greedy MIS algorithm. Let us first discuss the clustering of high degree nodes. The idea is to define a set H of high degree nodes, form trivial clusters containing only 1 node from these high degree nodes, and then call a clustering algorithm on the remaining graph. The approximation given by such an algorithm is actually only dependent on how big a degree we decide to set aside and how good the clustering algorithm called is. The idea behind the result is quite simple. Since the arboricity is bounded, high degree nodes have sparse neighborhoods. Hence, forming a cluster with a high degree node and its neighbors would produce a lot of negative disagreements by including all the negative edges in between neighbors. The best we can do to keep the disagreement as close to the disagreement of an optimum in any graph is to not include any neighbors. Let's now talk about our result on MIS. In order to design a fast algorithm for greedy MIS in the MPC model, we use this result by Fisher and Nover, stating that in the MPC model, solving greedy MIS can be done by each node, knowing only its O of log n hop neighborhood. So if you remember the graph exponentiation trick, we will only need to gather neighborhoods of size O of log n for each node. If we have 1 machine per node, then such a neighborhood can fit on 1 single machine, but getting this number of machines down and lowering the amount of global memory requires a lot more effort. Here is our main algorithm for greedy MIS. Notice that it runs in O of log delta phases, each executing a subroutine solving MIS only on a prefix of the graph. The algorithm works in the following way. First, a random permutation of the nodes is fixed, which is the only random part of this algorithm. Once this is done, the first term of the permutation allows us to define a prefix graph G1. A subroutine is then called on this prefix graph to solve MIS, and a new prefix graph G2 is then processed. This goes on until the entire graph is processed. Notice that in each subgraph DI, the maximum degree is O of log n. Also, notice that this algorithm runs in log delta phases because the size of the prefixes doubles at each phase. This is due to the fact that after each phase, the maximum degree in the remaining graph HI halves with high probability. Here is the first simple subroutine that we designed. It just uses graph exponentiation, as shown earlier, to gather neighborhoods of the prefix graph large enough to brute force a local MIS on each machine. This allows us to compute this MIS for each outer phase in O of log n plus log delta rounds. The total memory used with this approach is n to the 1 plus delta, since we assumed 1 machine per node. It is possible to reduce the global memory to m log n by using an alternative subroutine, but it makes the time complexity slightly worse. Let me give you a high-level idea of this alternative subroutine. This subroutine doesn't directly gather neighborhoods from the prefix graph, but will work in inner phases, and each inner phase will be cut into chunks. Dividing each phase into inner phases and each inner phase into chunks, on which the MIS will be successively computed, allows us to only deal with small enough connected components. Indeed, the connected components of every chunk inside an inner phase are of size O of log n. Hence, the connected components can be gathered entirely on one machine, and MIS can be computed locally. The subroutine requires a higher number of rounds. We also needed to make sure that after the subroutine has processed an outer phase, which is the prefix of the algorithm 1, the degree drop is still sufficient for the main algorithm to run in O of log delta phases. Actually, after one chunk is taken care of, the probability of the maximum degree dropping by half is only constant. But once an entire inner phase is processed, this degree drop happens with high probability with respect to delta. Finally, once all the inner phases of a phase of algorithm 1 are processed, the degree drops with high probability with respect to n. So after all these efforts, we get our main results by first clustering the high degree nodes and then simulating pivot on the remaining graph by using the described greedy MIS algorithm. We get a 3 approximation algorithm that runs in O of log delta, poly log n MPC rounds in the sublinear memory regime. Here are some open questions that remain open so far. The 2 first ones dealing with the MIS problem only. The first one is about computing MIS when the maximum degree is O of log n. Would this allow us to compute the MIS in O of log n rounds? The second one is about lowering the round complexity of greedy MIS in the MPC model without conditions on the maximum degree. Finally, the third one is about finding better algorithms for correlation clustering. Can the approximation be strictly better than 3 by minimizing disagreement? And can the guarantees be better than in expectation? So could we get a worst case guarantee? Thank you for listening.